the 30-minute call from the cockpit. You've heard it 100 times. Cabin crew, please prepare for landing.
E1, rotate.
And like everyone else, you assume the pilots are just sitting there, hands resting on the throttle, waiting for the runway to appear through the windshield. You might even picture them sipping coffee, flipping through a checklist, bored by the routine. That assumption is wrong in ways that reveal the most densely engineered 10-minute period in all of aviation. If you've ever watched the wing flaps extend and thought, that's just a metal plate moving, you were looking at a visual illusion. What you saw was the opening of a hydraulic sequence more complex than most factory assembly lines, and the process that drives it begins long before that metallic hum catches your ear. What actually happens in those minutes is not a lazy descent. It is a choreographed crisis of preparation, where a 300,000-pound machine systematically converts itself from a cruising jet into a landing vehicle. And every single system on board undergoes an identity change within that window. The cabin lights may dim, the seatbelt sign chimes, the engines spool down. These are not random actions. They are the visible layer of an invisible transformation that the pilots are flying, not just monitoring. Here's what the evidence shows. The approach and landing phase, defined as the final 10 minutes, accounts for roughly 4% of total flight time. Yet, according to NTSB data analyzed across the last 2 decades, nearly 48% of all commercial aviation accidents occur within that window. That is not a coincidence. That is a statistical signal pointing directly at the most cognitively demanding block of a pilot's entire workday. Now, consider what that means for the 2 people sitting behind the cockpit door.
Landing checklist complete.
They are not on autopilot, not in the way you think. They are managing a cascade of interdependent systems, each with its own failure mode, each requiring a precise sequence of inputs, each change monitored by instruments that are themselves being cross-checked by a second human brain. The first thing that happens during those 10 minutes is not a physical action. It is a mental shift. The pilot flying and the pilot monitoring transition from cruise mode, a low workload, high monitoring state, into an approach mindset. This is a documented phenomenon in crew resource management studies. The brain reallocates attention from general awareness to narrow focus. Peripheral scanning narrows. Reaction time expectations compress. The tone in the cockpit changes, and anyone listening to the intercom can hear it. But here's where the system itself starts to reveal its hidden layers. The aircraft's flight management computer begins executing what engineers call the approach transition. It recalculates vertical profiles, adjusts speed targets, and cross-references the landing runway's localizer and glideslope frequencies. If you have ever sat on the left side of the plane and noticed the control wheel making tiny autonomous corrections, that is the autopilot intercepting an invisible radio beam you never knew existed. The Instrument Landing System, or ILS, broadcasts 2 separate signals from the runway threshold. One defines the lateral center line, the other defines the descent angle. The aircraft locks onto these signals with a precision of less than 1 degree. And the pilots are monitoring this lock with an intensity most people reserve for surgery. And yet, most passengers never even notice that invisible beam exists. They simply feel the plane begin its final turn, unaware that 2 ground-based radio signals are being chased with surgical precision. That kind of hidden logic is exactly what this channel exists to expose. If you want to see through every hum, click and vibration next time you buckle in, subscribe and keep looking deeper. Before we move to the hardware hiding under the nose, drop the word ILS in the comments if you had no idea the runway was broadcasting a guidance beam at you this entire time. Remember that radar antenna you saw under the nose during boarding? That antenna is not for weather. The weather radar sits in a different location. That nose antenna is part of a separate system, the localizer and glideslope receiver. It is a passive antenna. It does not transmit, it listens. And in those final 10 minutes, it is the most critical sensor on the entire aircraft. If you have ever glanced at the window during descent and noticed the runway still looked distant, but the flight attendants had already stowed the carts, you witnessed the coordination gap between passenger perception and cockpit reality. The flight attendants do not wait for the wheels to touch. They wait for a specific announcement, but also for a sensory cue. The change in engine sound that tells them the aircraft has started the final landing configuration. That final configuration is not a single event. It is a sequence of physical transformations, each one creating a new load path through the airframe. The flaps are the most visible. When you see them extend, they are not simply increasing drag. They are reshaping the wing's chord line and camber, effectively turning a high-speed cruise airfoil into a low-speed, high-lift airfoil. The leading edge slats deploy simultaneously, creating a slot that accelerates air over the top of the wing, delaying the stall boundary. That is not a safety margin. That is the difference between flying and not flying at 200 knots. And here is where the engineering becomes almost musical. The flap deployment schedule is calculated by the flight control computers. They do not deploy all at once. They extend incrementally in stages called detents. Each detent corresponds to a specific configuration, a specific target speed, and a specific load limit. The pilot selects the flap lever position, and the computers govern the rate and position. If you ever sat by the window during approach and saw the flap mechanism moving in jerky increments, that was not a malfunction. That was the system following a pre-programmed ramp sequence designed to prevent aerodynamic overload. The spoilers, or speed brakes, deploy next, but not fully. They rise only a few degrees at first, reducing lift without dumping it entirely. On some Airbus models, the spoiler deflection is asymmetrical. The spoilers on one wing rise slightly more than the other to assist with lateral control during crosswind landings. You did not see that asymmetry. The difference is less than 2 degrees, but the aircraft felt it. Now, the landing gear. That heavy thump you hear and feel is not the gear locking down. The lock happens hydraulically, inside the wheel well. What you feel is the sudden redistribution of mass as the gear extends into the airstream. The drag increases instantly by roughly 15%. The aircraft decelerates without the engines changing power. And with the gear down, a new system wakes up. The anti-skid braking computers initialize. They perform a self-test that takes less than 2 seconds. If the test fails, an amber warning illuminates on the overhead panel, and the pilots must switch to an alternate braking mode. A backup system that operates with reduced capability but still meets certification standards. That self-test happens every single landing on every commercial aircraft built since the 1960s, and you have never known it was running. The landing lights come on, not for illumination. The landing lights are designed to melt ice. The halogen bulbs generate enough heat to prevent ice formation on the leading edge surfaces during the final descent through cloud layers. They also serve as a visual beacon for other aircraft. But the thermal function is the primary engineering purpose, and it is written into every maintenance manual. Now we enter the final 2 minutes. The autopilot can remain engaged down to a specific altitude, typically between 250 and 50 feet, depending on the operator. Below that altitude, if the autopilot is not disengaged, the aircraft will automatically disconnect it. This is called the autopilot height gate, and it prevents the aircraft from flying an automated approach all the way to the runway without human intervention. The disengagement is not a button press. It is a mental shift. The pilot who was monitoring now becomes the pilot who is flying. The hands that were resting 4 inches from the yoke now grip it. The eyes that were scanning the instrument panel now shift outside. The vestibular system recalibrates from instrument reference to visual reference. You just felt it. That moment where the brain switches from scanning instruments to gripping the yoke, from watching to flying. That split-second recalibration is invisible to every passenger on board. Yet it is the most critical transition in the entire approach. If you want to keep decoding these hidden layers that transform the way you experience every flight, subscribe to AV2, because the next time you see the landing lights come on, you will know exactly why they are burning. And tell us in the comments, what is one system or procedure you now see differently after this breakdown? And this is the moment where the system exposes its deepest secret. The aircraft does not want to land. The wing wants to keep flying. Every design decision that made the plane efficient at cruising altitude fights against the landing. The pilot is not flying the plane onto the runway. The pilot is forcing the wing to stop flying at the exact moment the tires contact the pavement. At 50 feet, the pilot begins the flare, a gradual pitch-up that reduces the descent rate from approximately 600 feet per minute to near zero. The aircraft is now in a transition state between flying and rolling. The wings are still producing lift, but the lift is decaying as the angle of attack increases and the airspeed decays. The touchdown should occur within the first 1,000 feet of the runway at a sink rate of less than 120 feet per minute. If the sink rate exceeds approximately 240 feet per minute, the landing is considered hard and a structural inspection may be required. Now, the reverses. The engine cowlings open, redirecting exhaust forward. The aircraft decelerates with a roar that passengers often misinterpret as engine trouble. It is the opposite. The engines are operating at full reverse thrust, creating a braking force that can exceed the wheel brakes themselves at high speeds. Below 60 knots, the reversers are stowed. The brakes take over. The anti-skid system pulses the brakes dozens of times per second, each pulse micro-optimized for grip. The system is identical in principle to the anti-lock brakes in your car, but it operates at hydraulic pressures exceeding 3000 psi, with response times measured in milliseconds. And in the cockpit, at wheels down and reversers deployed, the pilots are still flying. The nose wheel steering is not active until the tiller is engaged. The rudder is still controlling directional stability. The engines are still spooling. The crew is still scanning the instrument panel for amber lights that should not be lit. The landing is not over when the wheels touch. The landing is over when the aircraft reaches taxi speed and the pilot announces, 60 knots, I have control.
60 knots reach.
So next time you feel that gear thump, those lights flicker and the seatbelt sign chime, you are not in a routine descent. You are inside a high-stakes, multi-system transformation that was certified, tested, and flown by 2 people whose cognitive workload in that 10-minute window exceeds anything you will experience on the ground. And now you understand why the first thing the captain does when the parking brake is set and the engines are off is not a sigh of relief. It is a glance at the other pilot. The unspoken recognition that the most dangerous part of the flight is behind them. And you, the passenger who paid for a seat and got a front row view of the most brilliant engineering hidden in the plain sight, you just watched the invisible unfold. Comment which part of this sequence made you see the landing differently. I will read every response. Stay with me here, because the system that saves your life when an engine fails at cruising altitude, the one you have never heard of, handles its final check during those same 10 minutes. And that story will change how you hear the sound of an engine spooling down on final approach. The same engine that powers you through the sky at 35,000 feet must, in those final moments, be capable of reversing its thrust entirely. That transition is not a switch. It is a 3-second mechanical sequence involving translating sleeves that slide aft to block the fan duct, redirecting air forward through cascade vanes. The thrust reverser doors are locked by hydraulic actuators that must overcome the force of the engine's own exhaust to deploy. And these doors are monitored by proximity sensors that report their position to the flight deck within a fraction of a second. If even one reverser fails to deploy symmetrically, the aircraft could yaw violently on landing. That is why the pilots test the reverser system as part of the pre-landing flow. A silent confirmation that every door is ready to redirect the force of 800 miles per hour of accelerated air. And the brakes themselves. You see them as discs inside the wheel assembly. But they are not. They are carbon-carbon composite stacks that can withstand temperatures exceeding 2,000 degrees Fahrenheit during a rejected takeoff. On landing, the initial braking torque is not applied by the pilot's foot. It is applied automatically by the auto brake system, which the pilot selects before descent. The auto brake can apply maximum braking force within the first second of wheel spin up. Without any pilot input, the pilot can override it, but the system's reaction time is faster than any human's. The NTSB has documented incidents where the auto brake system arrested an overrun that would have been fatal without its instantaneous response. Now consider the tires. 16 ply rating, inflated to approximately 200 psi, they carry a load of over 50,000 pounds each during landing. They spin up from 0 to over 170 miles per hour in less than 1 second. That rotational acceleration generates temperatures in the tire carcass that can exceed 300 degrees Fahrenheit. The tires are not designed to last a specific number of landings. They are designed to survive a single land speed event repeated hundreds of times. And every single one of those landings is recorded in the maintenance log. Because the tire's performance in that final second determines whether the aircraft stops safely on the runway or continues into the grass beyond. The landing gear itself absorbs the vertical energy through oleo-pneumatic struts, a combination of compressed nitrogen and hydraulic oil that converts the kinetic energy of the descent into heat dissipated through the strut's internal orifices. The compression stroke on touchdown can be over 16 inches, depending on the aircraft weight. The strut must compress slowly enough to prevent bounce, but quickly enough to absorb the full vertical load before the wing's residual lift decays and the entire weight of the aircraft settles onto the gear. That balance is engineered into the strut's internal metering pin profile. If the metering pin is worn, the strut will bottom out, transmitting the full impact load into the airframe. And that metering pin, worn by fractions of a millimeter over thousands of landings, is the difference between a smooth stop and an airframe inspection. If you want to see the hidden tolerances that keep you safe on every single flight, subscribe, because the next video will reveal what the cockpit doesn't tell you about brake temperature limits and why pilots sometimes deliberately slow down on the taxiway. Comment with the word oil if you already knew the strut was filled with compressed nitrogen and hydraulic fluid. Let's see who else has been paying attention to the gear. And after touchdown, the spoilers deploy fully, not gradually as they did during the descent, but all at once, within half a second of both main gear wheels spinning up. This is called ground spoiler deployment. It dumps the remaining lift from the wings, transferring the full weight of the aircraft onto the landing gear, which maximizes the braking friction available from the tires. If the spoilers fail to deploy, the aircraft will float down the runway, unable to transfer weight to the wheels, and the brakes will be virtually useless until speed decays naturally. That is a scenario the system is designed to prevent, and the flight computers monitor wheel spin-up data to trigger the spoilers even if the pilot forgets to arm them manually. So the next time you're rolling out on a wet runway after a hard landing, and you feel the deceleration press you forward into the seatbelt, you are inside a multi-system chain that responds faster than thought, with redundant backups for every critical failure. And you did not know any of this was happening. You were just waiting to unbuckle and grab your bag. But the most impressive part of the entire landing sequence occurs before the wheels even leave the gate. The system that ensures the aircraft brakes have enough pressure to stop you is not tested in the air. It is tested on the ground by the ground crew during the turnaround. And that test uses a fluid you never think about, the hydraulic fluid that also powers the landing gear retraction, the nose wheel steering, and the flight controls. The hydraulic reservoir on a Boeing 737 contains approximately 7 gallons of fluid, pressurized to 3,000 psi by 3 separate pumps. During the landing sequence, the landing gear, flaps, spoilers, brakes, and nose wheel steering all draw from that same reservoir. The system must maintain enough pressure to support all these demands simultaneously. If the reservoir level drops too low, a low pressure warning illuminates in the cockpit, and the pilots must activate an electric backup pump that draws fluid from a separate, smaller reservoir housed inside the left main gear wheel well. That backup reservoir is your last line of defense. It holds less than a gallon of fluid, but it is sufficient to operate the brakes for a single landing and taxi-in. The NTSB investigated a 2018 incident where a main hydraulic leak forced the crew to land using only that backup reservoir. The aircraft touched down, braked, and taxied to the gate without any other hydraulic system available. The flight attendants reported the passengers applauded the landing. They had no idea the aircraft had flown the entire arrival with a single pint of fluid between them and a brake failure. This is the hidden architecture of every commercial flight. Not just the visible flaps, the audible gear thump, or the chime of the seatbelt sign, but the invisible cascade of systems that are tested, monitored, and deployed in a sequence timed to the second. And every single one of those systems is designed to work when everything else has failed. The aircraft does not want to land, but the system that makes it possible to land safely, repeatedly, reliably, in all weather, at night, on short runways with crosswinds, is one of the most undervalued engineering achievements in human history. And it all happens in the final 10 minutes.